Welcome to 3 lectures on coupled heat and moisture transport, where we're going to talk about how those transport forms influence one another. From that lecture, the first third of the themes that I'll talk about is here about the transient heat flow. And it goes along with the way of talking about 3 types of equations that we'll show. A transport equation and a continuity, or you could call it a balance equation. And then a third type of equation that binds the first 2 equations together, as you will see soon what I mean by that. This is the system that we talk about heat flow. And in the second part of what belongs to this theme, to this lecture, we talk about something similar for moisture flow, where we also see how heat and moisture influences one another. And then in the third part, we'll see how moisture has an influence on heat flow. But we take those 3 parts separately, and now this is the third part, where we talk about heat flow, isolated scene here, just to introduce the topics of those 3 equations. So first we start with heat conduction, governed by Fourier's law. And Fourier's law, we can say that if we are, let's say, within the material in a superficial surface layer inside the material, then the heat flux, watt per square meters, can be calculated according to Fourier's law, driven by the temperature gradient, multiplied with the thermal conductivity. So that's the heat conduction parameter or property of the material. So this gives us the transport equation. That's our equation number 1. Our second equation, to calculate these things in a transient mode, then we should set up some balances. So the second expresses a heat balance. And a heat balance we have to express for volume still within the material where we are. But in the volume, we have, from the left-hand side, we have heat coming in on the left, yes, and somewhat the same, plus a little increment that's leaving on the right-hand side. We focus only on one-dimensional conditions here in this lecture here. So we don't consider the y and the z directions, only the x direction, one-dimensionally. We keep track of the enthalpy content in the material, and we know that, as the first equation said, that the temperature is what drives the heat conduction. So that's our driving potential for this. Now, to set up the enthalpy balance, it says that the increment per time of enthalpy within our volume here, this we can calculate by taking the flux that enters, the heat flux that enters on the left-hand side, and subtract from that the heat flux that leaves on the right-hand side. That's a flux, so that's watts per square meter. So to have it as enthalpy for this box, if you will, then we should multiply with the surface area. So this expresses our heat balance in a time-intensive manner. So it's per time, because we're talking about fluxes in the unit of watt per square meter. So this is our equation, but now we'll manipulate a little bit with it. So rather than talking about the total enthalpy within the volume, then I'll talk about the specific enthalpy, so that's enthalpy per mass, and that we do by multiplying with the mass of the volume here. The mass of the volume, that's the density of the material that we are looking at, times the volume of the volume, and the volume of the volume, that's the area, times the thickness of the small box that we have here, so that's A times dx, and then again dH dt we carry on with. And then the right-hand side of the equation, we still have down here. Okay, so that's our continuity or our balance, but let's clean it up a little bit, guys. So let's see, something we can eliminate here. So first of all, we have an area here and there, so we can take those away. I also cleaned away what we had on the left-hand side. Also, we have 2 fluxes which are the same, only the increment we are interested in. So also that we can clean up. dx we have on both sides of this equation sign and can also be eliminated. So we are now left with this equation here, rho dH dt and dq dx. That's all what we have. So let's focus on that. That we do here. Here it's written again. So that was our heat balance in a mathematical form, and we saw the explanation on the previous slide. Now, this heat balance, it expresses here something with a specific enthalpy, and it considers the heat flux that we got from Fourier's law. So Fourier's law was driven by temperature And here we have the specific enthalpy. And we need somehow to know how temperature and specific enthalpy, how they vary with one another. And that's exactly the purpose of our third type of equation, the so-called equation of state. So it says that for every change of temperature, then we have a proportional change of specific enthalpy, and that comes with the heat capacity or specific heat of the material in case. So that's our way to introduce something that we, to be systematic, we call an equation of state. Now we can go back to our first equation, the Fourier's law, and then try to insert Q in the place up here, and we can also use then the equation of state. So let's see how we can combine all the things we have on the screen at this moment here. When we do that, when we insert Fourier's law on the right-hand side, as we had it before, well, then it comes lambda times dt dx. And over here, we replace the small h, the specific enthalpy, with c times dt. So this is our combined general heat conduction equation, where we have expressed everything in temperature by using all the variables and equations we had just on the previous slide. So that's our general heat conduction equation. We can also sometimes, if the parameters for thermal conductivity, specific heat, and also density of materials, if they're all known constant, and if they are constant, then we can comprise those parameters in one number. We call it A, which is the thermal diffusivity. And here is how it should be calculated. As a diffusivity, always it has the unit square meters per second, so that's also a thing to remember for diffusivity. And that more or less completes this little part of the lecture here with the thermal conduction only in a transient manner. Only this is an equation we can use if we're interested in heat only, so that's why I frame this as an intermediate result from the lecture. But soon we should carry on doing something similar for moisture and to see also about combined effects. But thank you for this little part to start with.